Welcome everyone to the 2025 Photonic Spectra Summit Series. Thank you so much for attending the Spectroscopy Summit, and in this session you will hear from Bill Choi, who founded Nano Lambda in 2005 with a vision of creating affordable measurement systems. Bill earned his degree in physics and spent 17 years working for Samsung Electronics. Today he joins us to discuss optical spectroscopy while also highlighting some future trends and market potential. If you have any questions or comments, you can type them right into the Summit chat box that is on your screen. And if you missed part of today's sessions, you can always come back later and watch them on demand. That's all from me. Bill, we appreciate you for taking the time to join us.
Thank you, Jake. Thank you, Spectral Media, for this great webinar opportunity. I'm very excited to introduce the revolutionary digital nano spectrometer technology. Nano Lambda is a startup company in Korea, the spectral sensing company. We pioneered this revolutionary digital computational spectrometer technology. After over 15 years tenacious efforts, we successfully developed digital nanotechnology and introduced first engineering sample, and currently more than 500 B2B customers purchase samples and development kits for their own test and evaluation and application development. We are honored to receive SPIE Prism Award in Smart Sensing category in 2021. And as a still startup, we are currently in the phase of raising funds for mass production scale-up. Spectroscopy is a science tool to detect materials. Even the James Webb Space Telescope is equipped with a very powerful multiple spectrometers. Scientists study spectral fingerprints to analyze what atoms and molecules are present in the stars, exoplanets, and galaxies. Not just for the space science, spectroscopy has been widely used in many industries for decades, but only in the lab by scientists, because the spectrometer equipments are too big and too expensive. Why? It's because the industry has been using basically the same light dispersing technology, prism and grating, over the last 300 years, after Isaac Newton first demonstrated the rainbow colors using prism. It requires distance and delicate optomechanical components and precise alignment. Compared to the electronics like a photodetector or image sensor, the optics in spectrometer is like an elephant. Then the question is how to put an elephant into a refrigerator. It sounds familiar, reader, right? There could be many different creative answers to this kind of riddle. So since these potentials are huge, becoming huge, there have been actually lots of efforts to miniaturize the spectrometers using many different technologies. But there is no tangible commercial products yet for personal everyday application. Thankfully, in 2021, one Science magazine article summarized and categorized these different approaches very well and clearly. The first one is dispersive optics, and narrowband filters, and Fourier transform, and reconstructive. Let's take a look at one by one. Hamamatsu Photonics in Japan, as one of the traditional spectrometer vendor, has used MEMS grating technology to miniaturize the size and developed micro series and SMD series as a commercial products. But it still requires distance and alignment, and as it goes smaller, the wavelength range and resolution will be coming issues. Another one, chromation, a spin-off from Columbia University in US, also used a photonic crystal instead of grating. As you can see here, similarly, it still requires distance and alignment and same issues. In 2000, filter array-based spectrometer on a chip first was demonstrated using 16 different Fabry-Faro filters, which means 16 different heights of mirror. After this, many research institutes and companies followed this Fabry-Faro filter array approach. IMEC made 32-channel Fabry-Faro filter array, 32 different heights of mirrors. In 2017, Viavi and EPC demonstrated 64-channel Fabry-Faro-based spectral sensor at Photonics West. But to make the 64 different heights, they have to use 7 different binary space layers. But controlling the exact thickness across the whole wafer must be very challenging. So maybe for that reason, no commercial product followed. Another vendor, AMS, now AMS Osram, also developed 64-channel Fabry-Faro filter array-based spectral sensor, and they introduced the commercial product. But for some reason, the product now was disconnected. Maybe due to the mass production yield issue, just my guess. So AMS has another approach instead, using interference filter array technology. Number of channels are somehow limited, but only goes up to 14 channels. Each channel filter spectral shape looks very narrow, very nice, but it requires around 30 layers for each channel. And each channel has different layer structures. It would be very challenging, but surprisingly, it's actually very amazing to make such 14 different channels on a single chip. But issue might be number of channels would be limited going forward. To overcome such issues, another approach was introduced, tunable Fabry-Faro filter. They use one single detector with a voltage-controlled moving distance mirror structure. Because it uses only one single pixel, the size could be very small. It's actually commercialized in the NIR range, but here we also have issues. Moving part itself would be an issue in many applications, and also high voltage to control the mirror distance is also another issue. So as we saw, each approach could have its own niche market, but due to the issues like required distance, nanoscale multi-height process on a wafer, and multi-layer process on a wafer, and moving parts, these approaches still cannot meet requirements for everyday applications. So now here we have totally different approach solutions. Digital nanotechnology. We Nano Lambda initiated, invented, and developed this technology. The first part of solution is a plasmonic nanofilter array. We make 1,000 different plasmonic nano-optical filter, all in a single layer. Single layer means from the cross-section view, the thickness and the structure of all are all the same for all filters. We control the wavelength transmissions using plasmonic nanostructures, shape, size, and pitches. in XY direction and lateral directions. As you can see on the upper left hand side, that's the nano filter array pictures. Some structures are circle and triangle and rectangular, or some plus signs and so on. So we control this shape and size pitches to make the wavelength filters. Each plasmonic nanofilter is assigned to each pixel, so that each pixel will selectively receive different wavelengths of light. The thickness of the filter array is less than 1 micron, as you see on the right hand side. It's a dielectric and metal dielectric structure. Because it is a single layer, the wafer process is also very flexible. So we are currently using nano imprint as a lithography because it's a relatively cheaper solution compared to other photolithography. First, we make a wafer scale mold and stamp, then simply press the mold and transfer the nano patterns onto the target sensor wafer 1:1 scale. Then we do etching process and so on. Here you see on the left hand side an 8-inch CMOS sensor wafer where a single layer plasmonic filter array is monolithically integrated and fabricated. It is a CMOS compatible process, requires just one additional layer, so it can be very low cost. As you see on the right hand side, one sensor has 32 by 32, actually 1024 filters, and the pixel pitch is 50 micron by 50 micron. So the optic area is only 1.6 by 1.6 millimeter, very small. This is the world's first plasmonic filter array based digital spectrometer. It's a small and low cost, but there is also a problem. The individual filter performance is not as good as other narrow bandpass filter technologies. As you see here, on the left hand side is plasmonic nanofilters, and on the right hand side it's interference filter, narrow band filter shapes. So it's a much broader and looks kind of ugly. So if we use nanofilter array only as is, the spectrum output will be totally different from the input light spectrum. Now we came up with the second part of the solution, digital technology. We invented the computational reconstruction method. Here we pre-measure the individual filter's transmission characteristics. Here are 1024 filter transmission characteristics. And then using low pixel data together with the pre-measured filter array information, then we calculate and estimate the input light spectrum. As you can see on the right hand side, the upper part is a low output, and the low output looks like just a noise. But on the bottom side, after digital processes, the input spectrum is beautifully reconstructed. Our first product covers from 340 nanometer to 1010 nanometers, very wide range using just one single spectral sensor chip. Here you can see some broadband light source measurement examples like halogen, white LED, and multiple LED light sources, accurately measured. Now we have a solution for everyday personal applications with no distance, no multiple heights, no multiple layers, no moving part, no hybrid assembly. So it's a very scalable platform technology 1,000 channels can be increased to 10,000 at almost no additional cost. Since NanoLambda published digital nanotechnology first, many universities started to follow the same approach with various ideas on nanostructure part and digital computational part, showing the possibilities of really small spectral sensor chips with a very high resolution and targeting the everyday personal applications. The research trend is growing very fast recently. In terms of a commercial product, other than the NanoLambda, there are also 4 other companies announced demonstrated computational spectrometer chip. 2 from China and also 2 from Europe. Those chips, spectral sensor chips, are all very small, and I believe going forward could become even smaller. So those computational digital nano spectral sensor chip is so small, it can be integrated into any wearable mobile or IoT devices, even kitchen faucet or even chopsticks. Now the spectral sensor will enable continuous health measurement by the people at medical grade accuracy, transforming the healthcare industry from hospital-centered to people-centered, possibly saving millions of lives and trillions of dollars. It's possible because, as you can see here on the narrowband scanning, there are some missing informations, and they are also scanning. The timing is all different for each channel measurement, so it's not uniform from the information perspective. But on the other side, the spectral measurement is a broadband. It covers all the information, more information, and just snapshot. So it's a much more noise robust. So it can enable clinically accurate multiple health information measurement. Now with a small and affordable spectral sensor, the blood glucose level can be measured non-invasively, and nationwide water quality can be monitored real time, and air quality as well. And you can tell whether food is fresh or not, or sweet or not. Total addressable market is huge, more than 5 billion units per year. Agriculture food applications are also very important and huge. Spectral sensing now can be used for liveness measurement, harvest time decision, and also photosynthesis measurement and nutrient and quality monitoring. Basically everywhere from farm to table. Nationwide, water quality can be monitored real time from water sources to kitchen faucet, telling you whether the water is safe to drink. And nationwide, air quality can be monitored real time in micro scale as necessary. It can also measure your skin and recommend right cosmetic products for you, and it can tell also your skin health status and skin aging status as well. Lighting is very important to humans, animals, and crops and plants. And digital spectral sensor will enable the continuous light spectrum monitoring to help maintain the best lighting conditions all the time for good sleep, health, emotion, productivity, and growth and yield, and so on. Actually, continuous light measurement is our first target application, and we developed our own application product, compact BLE spectral radiometer and recorder, which is very popular among research communities now, such as University of Oxford and EPFL, National University in Singapore and Queensland in Australia and UPenn in US and so on. Although it is still early stage, a few customers already developed and launched their commercial products, and we are also collaborating with many research institutes for application developments. And I can tell collaboration is our most important strategy for the commercialization. The market growth will be similar to the market growth we all witnessed during the transition from the analog film camera to digital camera to compact, affordable digital camera module. It's now everywhere. So same way, it will be explosive once the market accepts this new digital spectral sensing solution. If we look at the verticals in every applications, all the way up to spectral data and spectral data-driven opportunity, it will be more than exponential. It will be beyond exponential. So, in summary, as an astronomer said, if a picture is worth 1,000 words, a spectrum is worth 1,000 pictures. So whenever a spectrum is worth 1,000 pictures, there is opportunity. If you are interested in collaboration for this huge new opportunity, please let me know. We are ready to talk with you. Thank you. Thank you for your attention.
Thank you so much, Bill, for presenting compact spectroscopy technology for practical applications. To everyone that's joining us in the audience, if you haven't already, you can type your questions and comments into the Summit chat box, and do not worry, if you have not been answered yet, you will be reached via email at a later date. This session is hosted by us at Photonics Media, and we certainly hope you're enjoying the Spectroscopy Summit. Thank you all so much for joining us.